All right, we have integrated many different types of functions in this course, both indefinitely and definitely. However, there are a couple of questions that we haven't answered so far in regards to integrals. Namely, what happens if we integrate through a vertical asymptote? Is that even possible? For example, if we saw something like this, I gave you this function, and I'm missing a dx here. And I gave you this function and I said, all right, let's integrate this from 2 to 5. Well, I've already drawn out the graph for you here. And you can already get a sense that to try to even integrate this and to evaluate this definite integral from 2, you would be plugging in infinity. And one thing that I want to continue to reiterate here is that infinity is not a numeric value that you can plug in. It doesn't work that way in mathematics. You can't say infinity minus infinity is equal to 0. It's not a quantitative value. It's a concept to indicate kind of an unbound value in mathematics, not something that you can numerically plug in. So right away, we run into an issue like this. Or if I follow that up with, well, if we can't do that, or if I'm not sure yet how to do that, I should say, how would I do something like evaluating this from 3 to positive infinity? If I change the bounds of this integral from 3 to infinity, is this something that I can do? And the answer is it depends. And that is the question that I want to have us answer in Unit 7, Lesson 1. These types of integrals that we've just talked about are what are known as improper integrals. So we're going to start by actually looking at maybe a little bit of an easier example. So let's start by looking at a function such as 1 over x. So what we have here, and just so you can kind of see that function here, we're looking at the function 1 over x, okay? So in looking at this function here, we already know that the antiderivative of 1 over x is the natural log of x plus c. So if we wanted to integrate this function 1 over x, which would result in the natural log of x plus c, it would be equivalent to asking ourselves, the definite integral, I should say, would be equivalent to asking ourselves, what is the area underneath this curve? And if I wanted to integrate this from 1 to infinity, for example, because right now, again, we don't really quite know how to plug in something where there's a vertical asymptote at 0. So if I try to make it a little bit easier and just ask ourselves, okay, what's the area underneath this curve from 1 to infinity? Well, even that presents some issues because I could certainly plug 1 into the natural log of x, right? I could say the natural log of x minus the natural log of 1. The problem is trying to plug in infinity into the natural log of x is just not possible. What we can do as a workaround, however, is to evaluate the integral at increasingly larger and larger values of x, or our upper limit. So here's what I mean by this. If I were to go ahead and just say, all right, let's not get ahead of ourselves. Let's just see if we can even find the definite integral of this function, 1 over x, from 1 to 10. Let's just look at the area underneath this curve from, let me just kind of zoom out a little bit here, from 1 to 10, right? We seem to have finite values, numeric values that we can plug in. So we're looking at the area from 1 to 10. And that is possible. That would effectively just be the natural log of 10 minus the natural log of 1, which is approximately 2.302 or 303, depending on whether or not you're rounding or truncating. So, all right, that kind of gives us a sense of what's happening there. That is a finite definite integral. Now, what about if I increase that upper bound? If I increase that to 100, well, this then gives me 4.605, okay, another finite value. Well, let's bump that up to 1 to 1,000. Now we've also seen that our definite integral value is also increasing. And let's go even larger, 10,000, 9.210, or 100,000, 11.513. Now let's pause. What am I doing right now? What I'm effectively trying to do is I'm trying to figure out, can I get a sense of what the integral of 1 over x dx is from 1 to infinity, right? And because we can't plug this in, we know that this is going to be the natural log of x minus, excuse me, I should say, natural log of x evaluated from 1 to infinity, which we're looking at ln of x minus natural log of 1, right? And because we can't plug in infinity, we're trying to get a sense of what this might be by increasing that upper bound, by plugging in really large values for that upper bound and seeing if it gives us an approximation of what this definite integral might be. And if you maybe even want to rewind the video and just look at the values that we churned out, 2.3, 4.6, 6.9, now 11.5, what we're finding here is that all of these values are increasing and they don't seem to be settling in on a specific value, right? This integral then, we would say, would not appear to have a finite result. And another way of describing this integral, an integral that does not have a finite result, is to say that this integral diverges to an infinity. This particular integral diverges to an infinity, meaning if we try to evaluate this integral from 1 to infinity, we're seeing that it's not settling on a specific value. It's not approaching a specific value here. It continues to increase without bound. And you could try this on your own. You can continue to plug in numbers that are even larger, and you'd find that there's going to be no value that it's settling in on. So to maybe make better sense of this or another case, let's look at another type of function that may or may not do the same thing. So now let's look at the following function. And see, let's look at now g of x. So now let's look at g of x from 1 over x squared. Excuse me, of 1 over x squared. So it's a similar looking function, but we're seeing that there's going to be a little bit more of a dramatic behavior here since we're squaring the argument in the denominator. So let's look at 1 over x squared. Now, if we look at this particular definite integral, again, because we can't plug in infinity, we're plugging in a larger number for a bound. So let's start with something like 10. And then if we increase that upper bound to something like 100, we go from 0.9 to 0.99. And then if I increase that again, that gives us 0.999. And again, we get 0.9999. And you're starting to get a sense of what's happening here. This particular function, which again, let me write in a different color over here on the side, this particular function from 1 to infinity of 1 over x squared dx, this here, we're seeing that as we're increasing our bound, we seem to be settling in on a specific value. We went from 0.9 to now to 0.9999. I've lost track of how many nines I said. You get the idea, right? So we can say that this definite integral comfortably would result in a finite value. And that finite value is going to get very, 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 very close to 1. So close, in fact, that we can actually just say that this definite integral is 1. In this particular case, we would say that this type of integral does something called converging. It converges to a finite value. Specifically in this case, here it's 1. That value that it converges to is 1. So we've looked at two different types of improper integrals. And we call them improper because inherently there is a bit of an issue with us trying to use infinity as one of our bounds. The first one, we said that it diverges because it does not seem to be settling in on a finite value. The other one, 1 over x squared, we can comfortably say that it does converge, and it converges to a finite value, in this case, of 1. So I'm going to encourage you right now to pause the video and take a look at a couple of these functions here. And in these functions, I want you to try to make a conjecture as to whether or not you think these functions will converge, or excuse me, these integrals will converge or diverge. And you can do this by looking at the graphs. You can do this by just plugging in some values with your graphing calculator. But this is really just an exercise for you to kind of get comfortable with the idea of when a function would converge or diverge. Spend a few minutes doing this and go ahead and check your answers in the scan notes that I have uploaded. And in the next video, we'll actually start evaluating some improper integrals analytically instead of just playing around with some of the values and trying to make a conjecture based on what we're seeing numerically.